Okay, so hi everybody and welcome to this session. I'm Simone Severini and I'm grateful for this opportunity to talk today about the interplay between quantum physics and computing. The message that I would like to deliver with this talk is that the interplay between quantum physics and information processing is interesting. And it's interesting for two fundamental reasons. It's interesting because it can lead to new technology, but it's equally interesting because it can lead to new science. And as we know, the science of today is the technology of tomorrow. Now, the interplay between quantum physics and information processing is not a new area. In fact, it's over 40 years old, and it started in the 70s. But despite of that, today we are still very much just at the beginning. And today this area is often a topic of discussion in the media, mainly because of the volume of work that is done out there in quantum computing and quantum technologies. And this is the topic that I will consider today in my talk. And to do that, first of all, I would like to go back to the basic scientific idea behind the interplay between physics in general and information processing. This idea is very simple. Information is physical. It sounds trivial, but in my opinion, this idea is one of the most powerful ideas that have been introduced in science during the last century. What does it mean? What does it mean information is physical? It means that when we think about any communication device, we should not forget that it's made of matter. And so we should not forget that its behavior is governed by the laws of physics. Take a telephone, for example, or any other communication device. And the same applies to computers. Any computer built in the physical world is made of matter. And what computers can do and cannot do is ultimately determined by the laws of physics independently of the technology that is used to build that computer. It's a very powerful idea. Take an abacus, take any supercomputer out there, or even the brain potentially of a living organism. Now, it must be remarked that the computers that we use routinely and the communication device that we use routinely all functions today according to the laws of the so-called classical physics, which is a collection of physical theories that include mechanics, electrodynamics, thermodynamics, and relativity. And with this idea in mind, we can ask ourselves the following question. What is going to happen to information processing and information transmission if we change the laws of physics? What is going to happen to computers if we change the laws of physics? And the answer to this question is deep, as the question itself. Imagine, for example, that we could time travel. Is it possible? Is it not possible? I mean, I don't know. Nobody knows, right? But what we know is that if the laws of physics allows for time traveling, then this will impact computers, which is very interesting. It's very deep. Like, in what way? It's mathematically proven that if we could time travel, then a number of very hard computational problems would become easy. So in other words, a problem that would take centuries to be solved, all suddenly could be solved in minutes or in a reasonable amount of time, let's say. And an example is as follows. Given an arbitrary position of the Othello game played on an n-by-n board, the problem of determining the winner is known to be very hard. And the problem would be easy if we could time travel. Now, I've chosen here a rather abstract problem in my example, but other problems that would impact our lives because related to optimization and logistics are also equally suitable, just to mention a few areas out there. And so, if we change physics, we change computation. This is the message here. Now, without going into imaginary physics, like this physics that I consider here, we could ask, what happened to information processing if we consider quantum physics? And quantum physics is a very successful theory that describes the behavior of objects like atoms, which are the components of matter, or photons, which are the components of light. And quantum physics is then the theory that describes our reality at the fundamental level. But this theory, even if it's nearly 100 years old, is challenging to understand, and the meaning and interpretation of some of these aspects are still matter of debate. But quantum physics allows for two deeply interesting phenomena that can be applied to build technology. So the first phenomenon is existence of strong correlations. According to quantum physics, we can build two coins whose outcomes are correlated. This means two coins that whenever we flip the first coin, we get head. When we flip the second coin, we also get head. And the same for tail. Whenever we flip the first coin, we get tail. And when we flip the second coin, we also are going to get tail. So correlated. And this happens instantaneously and independently of the distance between the two coins. One of the coins could be here in Las Vegas, and the other coin could be in another galaxy, for example. And such phenomenon is at the basis of certain protocols for sharing cryptographic keys. I will talk about this later. And the second phenomenon is related to computing. Let's encode information in objects whose behavior is governed by quantum physics, like n bits in n atoms, for example, so 1 bit per atom. Now let's build a computer whose fundamental components are these objects, and the computation is a sequence of physical operations on the physical objects. This is called a quantum computer. And quantum physics allows for the generation of multiple computational paths that start from an input and somehow proceed towards all possible outputs. But the quantum computer amplifies the probability that the computational path that brings us to the correct answer at the end of the computation. And de-amplify, reduces the probability of the computational paths that bring us towards the wrong answers. And for the people in the room familiar with machine learning, think of quantum physics as giving an efficient representation of very large matrix multiplications. That's all, with minus signs, with negative numbers, for example. Let's forget about complex numbers. Or metaphorically, a kind of method for dealing with the curves of dimensionality through physics, which is very interesting. Now, let me go back to correlations. What can we build that can exploit the existence of strong correlations? Quantum networks. Quantum networks use quantum objects like atoms or photons to carry information. And the nodes of these networks can use these information carriers to share private randomness with each other. In other words, can share random bits that are correlated and can be known only to the sender and the receiver. So quantum networks enable two parties to share a random secret key which can be employed to encrypt and decrypt messages. And this can be used to protect information, and it can lead to engineer secure communication channels whose security is independent of the computational power of the eavesdropper. So it doesn't matter what computer the eavesdropper, how powerful the computer of the eavesdropper. And why this happens? Because security here is not based on the conjectural hardness of some mathematical problems, but on physics itself, on this idea of correlations, right? And technology to build quantum networks exists today, but not as large-scale deployments, and a lot of work still needs to be done in this field. And by the way, if you're interested on this topic, see the talk by David Levonian, SPC 301. The title is Entangled in the Cloud, Quantum Computing and Quantum Communication, today, this afternoon. It's going to be, I think, at 2:30 p.m., if I'm not mistaken. Thank you. Now, let's talk about quantum computers. So quantum computers are machines that use quantum physics for performing computation. And the scientific community uses the term classical computer to refer to any type of computer that is not a quantum computer, meaning any type of computer that uses classical physics rather than quantum physics. What is special about quantum computers? If you look at the set of all computational problems here, you will find evidence that there are problems that are difficult for classical computers, but that are easy for quantum computers. Where difficult and easy, it's really about time that takes to solve a problem. Now, there are problems that may take centuries to be solved on a classical computer, but that could take a much more reasonable amount of time to be solved on a quantum computer, like, let's say, minutes or days, like human scale, right? However, there is also evidence that not all problems can be solved more quickly by quantum computers. And indeed, there are problems that conjecturally are hard for both quantum and for classical computers. Okay, that's great. So where are we today with quantum computers? There are multiple approaches to build quantum computers, and each of such approaches has some obstacles to overcome. For example, there are approaches that use atoms, light, superconductors. Now there are also different types of quantum computers that are potentially useful for solving certain specific problems. But what is very important to keep in mind is that it's extremely hard to build quantum computers at scale. And when I say this, I mean that the problem of building a quantum computer at scale could be equivalent of going to Mars or realizing commercial fusion, right? So it's a really hard problem. And it's difficult because the components of a quantum computer are small-scale objects, nanoscale objects, are hard to control with high accuracy. And so quantum computers are prone to errors. In fact, quantum objects interact with the world outside. They interact with what is near them very quickly. And error for quantum computers means that during the computation, the computer starts doing things that we don't want them to do. And so we don't get the right answer, but a random one. And this is why it's so important to figure out how to correct errors in quantum computers, and this is a major challenge. Okay, it's fantastic. There is growing interest in quantum computers today, lots of interesting activity, but what is real about quantum computers? So in here is a pretty busy slide, but I've chosen here to highlight what is real about quantum computing by highlighting misconceptions, and by highlighting actually what is not real, right? So on this slide, I listed 10 misconceptions about quantum computers. So number one, quantum computers are useful in business problems today. So I personally don't know of any evidence of this. What I know is that on one side, quantum computers available today are still at the stage of prototype, and their best use is for learning about quantum computers of the future. I think this is a very important point. But on the other side, I see a lot of customers that are interested in quantum computing and want to understand the trajectory of this field and want to understand if and when a quantum computer is going to impact their business. Now, number two, quantum computers can break encryption today? No. The performance of current quantum computers is significantly below the level required to run algorithms that could break encryption, for example, RSA. I'm sure you're familiar with this topic, for example, and enable an attacker to decrypt encrypted data. But however, you see, it's important to start planning for the future and familiarize oneself with the various efforts to develop and standardize quantum-safe cryptography which is resistant against quantum computers, and key exchange protocols. And AWS is an active participant in this field and has already implemented candidate cipher schemes and made them available to customers as hybrid key exchange schemes with our own implementation of transport layer security. So quantum computers do not break cryptography today, okay? But it's important to look at the future. Number three, quantum computers are not small, right? The components of quantum computers are small, but quantum computers could fill entire rooms, in fact, probably entire buildings at some point. Now, number four, quantum computers will replace classical computers. I expect that quantum computers will be primarily accessed by the cloud and will be interpreted as coprocessors for solving very specific computational bottlenecks with mathematical characteristics that we are still learning about. Quantum computers will be able to solve some problems more efficiently, maybe on the basis of some structure that is in the problem itself. Now, number five and number six. So quantum computers give instantaneous answer and speed up every problem. Well, they don't speed up every problem, right? And do not give instantaneous answer on the basis that algorithms for quantum computers, that is, quantum algorithms, right, are a sequence of physical operations. And each operation has a time cost. So meaning that even a quantum computer would require a certain amount of time to solve a problem. Now, seven, what quantum computers, so quantum computer can be built without quantum physics. This is an interesting misconception, right? So it's the other side of the story, like the over-optimistic idea. Now, this is interesting. As far as science knows today, this is not the case, right? It's highly unlikely that quantum computers can be built without quantum physics, but it's not excluded, right, that quantum physics itself will turn to be an obsolete theory at some point, right? It's a physical theory, right? And theory changes and become obsolete. But today the scientific community does not believe that quantum computers can be built without quantum theory. And number eight, there are provable roadblocks to build quantum computers. I said multiple times it's very difficult to build quantum computers, but now this is about, is there some deep physical reason, some deep theory reason why we can't build quantum computers? Well, we don't have it yet. So, and there is no solid reason why it's impossible. So until then, it's possible to build quantum computers, right? Until we discover that reason. So number nine, you see, designing algorithms for quantum computing, it's easy. Well, that's not the case. So you can't just take an algorithm for a classical computer and translate it. It's very difficult to build quantum computers, but it's also very difficult to articulate use cases and to design quantum algorithms that can run in quantum computers. And this, you see, the bottleneck is not about programming. The bottleneck is really about the mathematically designed ways to solve specific problems. Finally, number 10, quantum advantage. What is quantum advantage? Quantum advantage, it's about something that a quantum computer can do that cannot be done with a classical computer. And usually people talk about quantum advantage when usually people talk about quantum advantage and speed, the time that it takes to solve a certain problem. But quantum computers potentially could end up to use less electricity than classical computers when solving the same problems. And this is something potentially very important that has nothing to do with time, but has to do with another fundamental physical resource, which would be energy. So quantum advantage could be about time, but could be about other dimensions, other resources. And quantum computing is a science, right? So this is a famous illustration that sometimes is used as an allegory for the scientific quest for knowledge, right? And I added myself these three bubbles, quantum world, classical world, and quantum computing. And from the scientific point of view, quantum computing is a necessity. A necessity means that if we really want to explore the ultimate physical limit of computation, we need to think about quantum computing. We can't forget about this. And that's why quantum computing is a science. It follows that quantum computers should be primarily interpreted as research instruments that somehow, by accident, may end up to be applied to business problems. And research instruments like telescopes, but for looking deeper into our physical reality. And quantum computers could change really fundamentally how we interpret the world, how we experience the world, how we collect data, and how we simulate quantum mechanical processes, something which is not computationally feasible with classical computers. So simulation that use quantum computers will define the area of in silico simulation of chemistry, which may eventually yield significant improvements in human health, maybe via pharmaceuticals, in agriculture, maybe via new fertilizer, or sustainability of our planet, maybe via energy storage, understanding how to better store and move energy. And these are all areas that require computing quantum stuff. And these are all areas that are difficult for classical computers, right? So quantum computers as a scientific instrument in first instance. I think this is a very important message. And the bottom line is that from now on, quantum computer science and the science of quantum physics will advance together, hand in hand. And it's amazing. It's a marvelous fact. Okay, so at this point, I've been talking for about 16 minutes, and you may ask yourself, why is this guy from AWS talking about quantum computers? At AWS, we are investing in the long-term potential of quantum technologies. And first, we created and launched a service that everyone can use. It's called Amazon Braket. Braket is a fully managed service that can give access to a variety of quantum computers today, built with different technologies. In this way, customer can design, test, run their quantum algorithms or real quantum hardware today, right? This is on demand, this pay-as-you-go, is generally available, and it's integrated in the AWS cloud. And you can use it, as I said, today. And we started building Amazon Braket. Why? Because customers wanted a window over the technology. They wanted a way to determine what is real and what is not about this field. And this is a service that allows customers to prepare themselves for the future and to understand what is the trajectory of the technology itself. Now, while the goal of Amazon Braket somehow is helping accelerate innovation, right, and discovery, I feel also that the Braket team is learning a lot about the complexity of integrating quantum computers in a complex IT infrastructure as AWS. And in this way, this is somehow an opportunity for AWS to prepare also for the future of quantum computing. And I believe the cloud is uniquely suited to making quantum computers accessible to customers. Now, second, we launched the AWS Center for Quantum Computing in 2019 in partnership with Caltech, the California Institute of Technology. And there is where we are researching and building our own quantum computers based on superconducting technology. And the center is really a key part of the AWS long-term vision for quantum technologies. And we do research and development, and our goal is to deliver a fault-tolerant quantum computer that can perform low-error computations at scale beyond the capability of classical computer technology. So long-term vision, building quantum computers that are useful for customers. And third, we help enterprise to engage with the technology. So we launched the Amazon Quantum Solutions Lab. This is a team of subject matter experts in quantum computing whose mission is to help AWS customers accelerate their interaction with quantum technologies and get ready for the future. And the Amazon Quantum Solutions Lab run collaborative research projects together with our customer using expertise in quantum computing, but also in machine learning, optimization, and high-performance computing. So in fact, when they work together with customers, they try to understand whether quantum computing at some point could be useful, but they work on what is available today as well, which I think is very important. Finally, fourth, we launched this week the AWS Center for Quantum Networking. This is where we are researching and building quantum networks, and we are doing this because, you see, it's important to build quantum computers, but also it's important to understand how to connect these machines together. And I think that this is an amazing opportunity, which is parallel to the effort for building quantum hardware and quantum processors, but I think is equally important and could lead to very interesting things that have to do with privacy in ways that today are still far in the realm, let's say, of quantum cryptography and distribution of correlations. Distribution of correlations that could allow a new level of privacy for customers. Now, an interesting question here is what customers are doing today, right? And as I said, customers are preparing themselves for the future. And here I wanted to mention specifically the BMW Group Quantum Computing Challenge, because it gives a bit of a feeling about what customers are doing. This is an initiative that I like very much. This was a challenge that BMW and AWS have run together, and it was concluded last December. BMW proposed some concrete problems, real-world problems, for example, simulation of material deformation in production or vehicle sensor placement, and AWS and BMW selected proposal to approach this problem, and AWS provided access to quantum computers. Applicant submitted proposal for solving these problems. It was a way somehow to crowdsource quantum solutions for real-world problems involving the community. And there were about 70 submissions from 16 countries. And the winners were announced last December. QCware, a startup from Palo Alto, California, 1QBit, Canadian startup, Accenture, and Q&Co, a startup from the Netherlands that recently merged with Pascal, a French quantum hardware startup. And I think that this challenge was very interesting because it really crowdsourced approaches to real-world problems where quantum computing can have a role at some point in the future. And we shouldn't forget that while on one side, again, it's very difficult to build quantum computers at scale, on the other side also, it's very difficult to articulate useful use cases and to feed problems to quantum computers. And the challenge, I believe, was a valuable step in this direction. It was an opportunity for people to think deeply about the field and start generating activity in relation to real-world problems. So I think it was a very successful experiment. And so now, what's your next step? So for the people here sitting in the audience. Now, quantum computing represents an opportunity, and like all opportunities, it raises questions, right? What does quantum computing mean for you? Where is the value now for your organizations? Obviously, anyone can participate. And here are 4 personas: quantum curious, quantum pioneers, quantum enablers, and quantum pragmatists. And the question is, how does success look like for me as an industry leader? And this question has a different answer depending which of these persona I am, right? And you are. And the quantum curious want to learn, want to read, want to explore, want to understand the state of the art of the field. Then there are the quantum pioneers. These are the people that hire teams, the people that commit resources, that engage the community, they sponsor research in academia, for example, trying to push the field itself. And then there are the quantum pioneers that are innovating directly. So in this group, there are the hardware builders, for example, and the researchers. And then another group is formed by the quantum enablers. See the startups, system integrators, educator, consulting. And these are in the higher level of the stack. And they built on quantum and help grow in awareness. And these are the people that also built on Amazon Braket and AWS. Right now, there are over 30 startups out there that are using Amazon Braket as integrated in the AWS cloud to build their business. And I think that this is very interesting. And finally, the last persona is quantum pragmatists. These are the organizations that, they don't really care about quantum computing as a field, but that care that quantum computing solves the problems that they need to solve. And in other words, it could be quantum, it could be classical computer as far as my problem is solved. And the quantum pragmatists are then technology agnostics, but they're problem-centric. And they usually decide to sit and look, waiting for the technology to evolve, or in other cases, they work together with professional services or consulting businesses and with quantum enablers to figure out if and when quantum computing will impact their business so that can be ready when that is going to be the case. You see, it's a long journey. And again, I think that the cloud is critical in making that journey a success. And I think that now is the right time to be ambitious and is the right time to engage, even if quantum computing is a journey that is more a marathon than a sprint. And I'd like to conclude my talk going back for a second to the scientific perspective, which I believe is truly important. And this is a quote by Charlie Bennett, a pioneer of quantum information processing. The greatest achievement of our field, which is quantum science, quantum information and computation, won't be to speed up computation, but to help people understand that this world is quantum mechanical. And I like this quote because some of the deepest forms of innovation are generated by the observation of our world. And quantum computers are a new instrument for observing our world, for exploring our world and our reality at the fundamental level. And I want to remark once again that it's very early days for quantum computing, that we need to have a long-term vision, a lot of patience, and we need to set the right expectation. But I want to say clearly that the future potential discoveries associated with quantum computing could be way far beyond our imagination. And with this, I'd like to thank you for your attention and for being here today. Thank you.